This simulation is going to help us to understand flow rate and how the area of a pipe can be affected, or how the area of a pipe can affect the rate at which liquid passes through a pipe. So here, if you look up here, you have the flow rate is measured in liters per seconds. So what you're calculating is how much stuff or how much of a volume passes by the edge of this pipe here each second. And if we increase the flow rate, so you see there, they're more spread out because the water is moving by more rapidly, so they can travel over a larger distance. So this one has a higher flow rate, more volume passes by per second here. So that's the flow rate. So now let's see let's also measure the velocity. So in this case here, the velocity should be the same throughout this entire pipe because the size of the pipe is the same. But now let's go ahead and change the area of the pipe and let's see what's going to happen. So if I make this cross-sectional area of the pipe larger, you notice that the flow rate drops. And if I make this same area smaller, the flow rate increases here. So the smaller the cross-sectional area of a pipe, the bigger the faster to keep the same flow rate, the particles have to speed up, so the bigger the velocity. And if you make the cross-sectional area of the pipe larger, to keep that same flow rate constant, that means that the velocity has to become smaller. So the smaller the cross-sectional area of the pipe, for the same flow rate, velocity is going to increase. And the bigger the cross-sectional area of a pipe, in order to keep the same flow rate, the velocity is going to decrease. So the next term is specific to medical equipment, such as syringes and respirators, but probably also to car engines. Imagine that you have a pipe, and then there's water flowing through the pipe, so that the water is moving down the pipe here. And we want to describe the rate at which the water flows. So let's see an instrument that would use something like that. It would be something like this, an automatic syringe where you can adjust the settings and you can push a certain amount of fluid and control how much medicine is given to a patient. So you want to be able to know exactly how much water or medicine flows through this pipe here. And the way you would do that is just to say that you're going to have a small section of fluid in here, and that fluid is going to take up some volume V. Actually, no, excuse me, thinking about the wrong thing here. This fluid is going to pass through this pipe, and this pipe is going to have an area A, and this fluid is going to be moving through the pipe with some velocity V. And from there you can describe, well, given the speed, it's going to travel over this pipe here at a certain rate. So the flow rate is just going to be the area of the pipe multiplied by the speed that the fluid flows through the pipe. And so the flow rate Q is going to have a couple of different units. It can be measured in cubic meters per second, because this is a volume here of fluid, or it can also be measured in liters per minute. So you just have to check your conversions there, where 1 cubic meter is going to equal 1,000 liters. So let's look at another device that uses that. This is going to be this device here, where you can actually change the size of these nozzles and adjust the rate at which a patient receives oxygen. So again, the area of the pipe is going to determine the flow rate. So the last one has to do with, for example, oxygen tanks. So let's say that, and how you want to measure the exact pressure inside the oxygen tank. So the way that this would work is, let's just, instead of looking at an oxygen tank, I'm going to look at a piston, which is pretty much just a tube with one open end and one closed end. And then you place a lid on that tube. And inside that tube, you're going to have a gas. So the gas is going to be hitting the walls of this tube. So they're going to apply a certain pressure, and that pressure of the gas, I'm going to call it the actual pressure. And if you want to measure yourself how much pressure a patient is going to receive, what you would do is, you wouldn't really do this, but you place your hand onto the lid, and you'd feel how much force you need to exert, or how much pressure you need to exert onto the tank to push it inwards. So we're going to call it the gauge pressure, the pressure that you feel. But along with that, there's going to be another pressure. There's also the air outside here, and the air outside is also pressing inwards on the lid here and helping you along. So this is going to be the pressure from the atmosphere, so I'm calling that one P atmosphere. So the pressure that you feel is going to depend on the pressure from the atmosphere and the actual pressure inside the gas. And so this pressure you feel, the gauge pressure, is going to equal the actual pressure of the gas inside the tank minus the pressure from the atmosphere. And so there's a couple different conversions. You can measure the pressure in atmospheres, where 1 atmospheric pressure is going to equal 1.01 times 10 to the 5 pascals. But you can also measure this in pounds per square inches, and there's other units out there. So you just have to watch out for that too. So this concludes the lecture section for chapter 13. Afterwards, I'm going to have you I'm going to solve some more word problems for you, and then after that, you'll do some word problems yourself.